At 6:49 on a February morning, a tree touched a high-voltage line in Northern Virginia. Protection cleared the fault current. After the reclosing sequence, the line locked out. Then 1,800 megawatts of data center demand moved off Dominion Energy's system. That is roughly the output of 2 large power stations changing sides within one protection sequence. Another 544 megawatts of cooperative load moved with it. The data centers did not cause the tree strike, and they did not lose power. Their controls moved them to backup when grid voltage failed their limits. Most electrical diagrams show power plants as active machines and customers as passive loads. At this scale, customer controls affect the grid too. A cluster of facilities can watch the same voltage signal, reach similar decisions, and move together. So the question is not simply why these buildings have backup generators, it is this: how does a grid stay stable when 1,800 megawatts of demand can behave like one machine? To answer it, we have to begin with an earlier fault, 6 voltage depressions, and 82 seconds that changed how Virginia connects large loads. At about 7 in the evening on July 10, 2024, a lightning arrestor failed on a 230 kilovolt transmission line in the eastern interconnection. The device normally shunts dangerous surges toward ground. Its failure left a permanent electrical fault on the line. The first response came from transmission protection. Relays detected the abnormal current and told circuit breakers to open. That isolated the fault. But many line faults are temporary. A branch can fall away, an arc can extinguish. So high voltage lines commonly use automatic reclosing. After a breaker opens, the system waits, closes the line again, and checks whether the fault has disappeared. The July line was configured for 3 automatic reclose attempts staggered at each end. Because the fault was permanent, each attempt energized the fault again. Across the sequence, the system experienced 6 short voltage depressions in 82 seconds. The shortest lasted 42 milliseconds. The longest lasted 66. In the area where load later transferred, voltage on the faulted phase fell to between 0.25 and 0.40 per unit. Then the breakers cleared each event correctly. From the transmission side, this was a protection sequence working through a bad line. No utility equipment disconnected the data center load. The fault was not inside a server hall. It was not even necessary for the line to feed a particular building directly. A fault changes voltage across an electrical area, and every sensitive facility connected to that area can see the disturbance. The grid did not order 1,500 megawatts to leave. Customer equipment responded to the voltage disturbance. Automatic reclosing restores many lines after a temporary branch contact or arc clears, preserving a valuable path without waiting for a crew. With a permanent fault, every test produces another sag. Transmission operators can see one line fault while facility controllers count several departures from their safe voltage envelope. That is why ride-through needs an agreed waveform. The campus must know the depth, duration, and normal number of attempts it should survive. July made the boundary measurable. 6 depressions lasting tens of milliseconds across 82 seconds. Requiring connection through any waveform would be unsafe, while transferring too early turns routine grid protection into a large loss of demand. The timing serves both sides. A line that remains open after every temporary contact leaves the transmission network weaker until crews investigate. A campus that treats every reclose as a long outage may run engines for hours after the line is healthy. Operators need enough attempts to recover the grid path, while customer controllers need one published sequence they can recognize as normal protection rather than 6 unrelated emergencies. A server does not experience a transmission event as a tree, an arrestor, or a breaker. It experiences voltage. Inside a data center, utility power passes through layers of electrical equipment before it reaches computing hardware. Switchgear divides the supply. Transformers change voltage. Uninterruptible power systems condition the power and bridge short interruptions. Batteries or flywheels cover the gap while generators start or another source takes over. There is no single universal design. NERC's incident review describes several broad arrangements. A static UPS can place a battery and power electronics between the grid and the load. During a brief disturbance, the battery supports the servers. If grid voltage returns inside the acceptable window, the system can settle back without a long transfer. Another facility may use a diesel rotary UPS, often shortened to DRUPS. A spinning machine stores energy in a flywheel. If the grid fails its tests, an engine takes over and keeps that rotating system alive. Once the facility has committed to that alternate supply, returning to the grid may require a deliberate manual sequence. The details matter because protection settings turn a voltage waveform into a yes or no decision. How low did voltage fall? How long did it stay low? How many disturbances occurred? How close together were they? Did the controller count a fault and the immediate reclose as one event or 2? In July, the first depression was not the whole story. The line opened, tried again, opened, and tried again. NERC found that facilities responded differently. Some rode through, some transferred briefly and returned. Much of the sustained loss appeared after the third voltage depression, when disturbance counting logic at multiple sites reached its threshold. The settings protected individual sites where a small power quality problem can interrupt computing or corrupt work. The grid effect emerged because many sites reacted to the same sequence. A campus transfers in blocks across electrical rooms, UPS trains, generators, and mechanical systems with different tolerances. Batteries or flywheels bridge only long enough for the next source to stabilize, and voltage, frequency, and phase must remain within limits during the handoff. Critical computing load may remain behind power electronics, while chillers, pumps, fans, lighting, and office systems follow other paths. A static UPS uses batteries and electronics to bridge a disturbance. A rotary design stores kinetic energy in a spinning machine until an engine takes over. Those arrangements can preserve the servers yet present very different amounts and timing of load at the utility meter. Returning can be harder than leaving. Operators may verify the grid, unload or synchronize generators, and close breakers in stages. Manual return spreads demand out, but is difficult to forecast. Uniform automation could create another synchronized step. Coordination therefore needs a return plan as well as a write-through setting. Power systems have to balance generation and demand continuously. Before the transfer, generators were producing enough electricity to meet the load. When approximately 1,500 megawatts disappeared from the grid, those generators did not reduce output at the same instant. For a moment, supply exceeded demand, so system frequency rose. The first visible result was frequency. In North America, the system is centered on 60 Hz. With more mechanical and electrical input than the remaining load required, frequency rose. NERC recorded a peak of 60.047 Hz. It settled back to 60 in about 4 minutes. Voltage also rose as less power flowed through the local network. It reached 1.07 per unit, below the level NERC considered a reliability risk in this event, but high enough to require operator action. Transmission systems use shunt capacitor banks to support voltage. They are especially useful when heavy power flow pulls voltage down. But if a huge block of load leaves, the same support can become too much. Dominion reported that operators removed 9 230 kilovolt capacitor banks within 7 minutes to bring the area back toward nominal voltage. Notice what operators were managing. The initiating fault had already been cleared. The emergency was not a server hall going dark. The operational task was absorbing the electrical consequence of customers protecting themselves. NERC says the July event did not create a significant reconnection problem, and voltage and frequency did not reach dangerous thresholds. That is essential context. This was not a near collapse disguised as a technical memo. The event stayed within reliability limits, but it showed planners a load loss mechanism that could be larger next time. A 1,500 megawatt transfer was manageable. A larger transfer, a less favorable generation pattern, or a badly coordinated return could produce a different result. Once planners know that a fault can remove this much demand, they have to study it like the loss of a power plant, only in reverse. Dominion's later technical presentation put the July transfer at 1,551 megawatts across 22 substations in the area it analyzed. Individual locations moved between 4 and 235 megawatts, with an average of 70.5. NERC used the rounded figure of approximately 1,500 megawatts. Public presentations use different counting scopes for substations and load points, so those totals should not be forced into false precision. The load was distributed across many connections, yet the same disturbance triggered similar responses. NERC estimated that about 1,260 megawatts remained off the grid for hours. Most of that sustained transfer followed the third depression. Different operators then had different procedures for returning. A static UPS might settle back quickly. A facility on long-term backup generation might wait for personnel, a stability check, a synchronization sequence, or a minimum generator run. From the building owner's perspective, staggered return can be cautious. From the system operator's perspective, uncontrolled return creates another forecast problem. If hundreds of megawatts reconnect together, demand can jump up almost as quickly as it fell. This is why the event cannot be solved by telling data centers never to transfer. Backup power is part of the resilience customers pay for. The useful question is how a facility distinguishes a routine, correctly cleared grid disturbance from the kind of sustained problem that truly requires a long transfer. That distinction became more urgent 7 months later. On February 17, 2025, at 6:49 in the morning, a tree struck a 230 kilovolt transmission line. Early public materials said the contact came from outside the right-of-way. The line went through its reclosing cycles and locked out. Once again, the initiating event was on the transmission system. Once again, customer controls watched the resulting voltage depressions. Dominion's early investigation described approximately 1,700 megawatts of data center load transferring. Later presentations revised the data center figure to 1,800 megawatts and added 544 megawatts of cooperative load. The data center portion affected 18 substations and 44 transformers. Reported transfers at individual locations range from 4 to 154 megawatts, averaging 75. Public slides do not name the substations. The detailed presentation calls the origin simply Substation A, and that anonymity needs to remain intact. The later technical record gives a sharper view of the fault. Dominion described a 5,000 amp phase-to-phase fault 2.84 miles from Substation A on a 6.42 mile line. Protection cleared it correctly in 5.9 cycles, or 98.53 milliseconds. The line used electromechanical impedance relaying, and the fault changed character during the reclose sequence. Most affected data centers transferred after the third reclose attempt. Some rode through. Even facilities belonging to the same customer did not always respond in the same way. That variation is useful. It shows that large load transfer is not an unavoidable property of computing. It is an interaction among the grid waveform, the facility's electrical design, its protection settings, and its operating policy. The public record does not disclose a definitive February transfer back time, an event cost, a peak voltage, or a responsible party for those costs. It does not support a story about a secret named substation. The second event repeated the mechanism with a larger block of data center demand. Engineers use the phrase common mode when systems that appear independent share a vulnerability or trigger. Dense data center regions can create a common mode without sharing an owner or a backup plant. The shared element can be the transmission voltage. It can also be a design convention. Facilities buy similar UPS equipment, follow similar protection practices, and optimize for the same goal. Never let unstable utility power reach the computing load. At a small scale, the grid barely notices. At Northern Virginia scale, identical caution can become a system event. There is also an information mismatch. A utility may know a customer's peak demand and contracted capacity without knowing exactly how the customer's controllers count disturbances. A planner may model the building as a block of load that declines smoothly with voltage. The real building may remain steady through 2 sags and then transfer almost completely on the third. That difference changes contingency studies. If the model assumes passive demand, it will underestimate the generation surplus after a fault. It may also miss the voltage rise, capacitor switching, and reconnection ramp that operators have to manage. The data center owner has a corresponding blind spot. Its protection study can prove the campus survives a disturbance without showing what happens when 20 other campuses run similar logic. No single customer controls the aggregate result. Traditional load models combine millions of devices into a manageable response. Power electronics can behave differently. Controls hold power steady as voltage falls, then a threshold removes a large block sharply. Planners therefore need dynamic models for voltage thresholds, timers, disturbance counters, backup transitions, and the ramp back, plus an estimate of how many facilities share a setting. That regional estimate matters as much as a precise model of one campus. A utility can know contracted demand without knowing whether 20 separate facilities count the same third depression. A data center owner can prove its own equipment survives without seeing how similar protections behave across the region. Neither party controls the combined result, so the study has to test plausible groups rather than one building in isolation. The details can remain protected without leaving planners blind. Utilities need validated models that can be tested against disturbance data, not a public map of every circuit. July and February now provide calibration points through the order of transfer, the load that stayed away, and the grid response that followed. Reliability now depends on coordination beyond the meter and contract. By April 2026, Dominion's facility interconnection requirements contained a detailed section for large power electronic interface loads. Data centers are specifically included. For qualifying projects, the utility now asks for site-specific load composition, ride-through capability, load profiles, backup power details, protection information, and reconnection behavior after a disturbance. Long-term projected demand above 50 megawatts is one threshold, although Dominion and PJM can study smaller loads when their characteristics or location justify it. The physical requirement connects directly to July. Under Dominion's current requirements for qualifying projects, these loads must ride through at least 6 automatic reclosing attempts lasting 50 to 70 milliseconds each. Dominion recommends reviewing short-duration voltage detection timers and, where appropriate, increasing them to roughly 80 to 120 milliseconds or more. The purpose is not to make a facility ignore real danger. It is to prevent a normal breaker operation from being counted as several independent emergencies. The guidance also calls for coordinated protection settings and enough model detail for planners to test how the facility behaves. That turns an invisible customer decision into something the grid can study. It also changes project development long before a building opens. Missing or incomplete dynamic models may require additional study or conservative assumptions. If later equipment changes alter the UPS, protection, or backup sequence, the model has to change too. A one-time interconnection study is not enough for a facility that expands in phases and replaces electrical equipment over decades. Monitoring can close the loop. Disturbance recorders show the transmission voltage waveform. Customer telemetry could, where agreed and protected, provide transfer timing for model validation without exposing the computing work. Controlled reconnection is the other half. Operators need a way to avoid a sudden return while generation is still being adjusted. That can mean staged blocks, minimum delays, a communicated ramp, or coordination through an operating contact. The exact method can differ by facility, but the regional result has to remain inside a studied envelope. None of this eliminates backup generation. It makes the boundary more explicit. The campus still decides how to protect its servers. The grid sets performance requirements for the way a very large customer enters, leaves, and returns to a shared system. The remedy has a practical order. First, qualifying facilities have to survive the normal reclose waveform. Next, planners need models that reproduce when each block transfers. Finally, operators need a studied return that avoids another abrupt change. Timers, telemetry, and model updates support those three outcomes. They are not the outcome by themselves. It still leaves hard choices. A timer that waits longer may improve ride-through but reduce the margin for sensitive equipment. A controller that returns automatically may help the grid recover but create risk inside the campus. A utility that requests detailed backup information has to protect commercially sensitive and security-relevant data. There is no single setting that fits every facility. Coordination means agreeing on performance at the boundary, what the load must survive, how it communicates a transfer, how quickly it can return, and how the aggregate behavior will be tested. The immediate consequence of these events was operational. Grid operators changed capacitor status and managed frequency and voltage. Facility operators ran batteries, flywheels, engines, or other alternate supply. Customers and utilities investigated why different sites reacted differently. The longer consequence is infrastructure. Coordination can require models, studies, operating procedures, and, at some sites, new controls or equipment. Those measures can carry costs, but the public records do not quantify them or assign them to the February event. The cost categories also occur at different boundaries. The utility may install recorders, change studies, or adjust transmission operations. A campus may revise controller settings, add telemetry, or replace protection equipment. PJM and neighboring utilities need models for the regional consequence. A fair allocation has to identify which work serves one connection and which improves a shared system before anyone turns a technical requirement into a customer charge. Virginia has also created a new large customer rate class for future service. The Commission says qualifying customers will face minimum payment obligations tied to contracted demand intended to protect other customers from rapid infrastructure build-out. That is a separate cost allocation response, not a verdict on who owes money for these incidents. The larger principle is the same. When one customer is large enough to change the system, its electrical behavior and financial commitments cannot remain private in every respect. Existing customers should not underwrite equipment built for demand that may move or disappear. At the same time, a data center cannot accept utility power without the right to protect its own load. The workable boundary is shared responsibility with measurable expectations. For qualifying future projects, Dominion's requirements cover ride-through, study information, and reconnection behavior. The 2024 and 2025 records do not establish compliance or non-compliance with that later standard. Regulators still have to decide who pays for the monitoring and upgrades that coordination requires. A stable grid has to model large data centers as active electrical systems, not passive demand. The buildings and owners remain separate, but shared voltage thresholds can make their combined response look like one machine. Planners need site-specific behavior, ride-through expectations, visibility during a transfer, and a controlled path back. The July 2024 event showed the mechanism. A failed arrestor created 6 short depressions. Customer controls moved approximately 1,500 megawatts. Operators handled the frequency and voltage response, and NERC found no reliability threshold was crossed. The February 2025 event showed that July was not isolated. A tree strike was followed by 1,800 megawatts of data center transfer across 18 substations and 44 transformers. The lesson is not that backup power is the enemy. Backup power did what the facilities expected. The lesson is that private resilience can create a public grid event when thousands of machines make the same safe choice at the same time. Dominion's April 2026 interconnection requirements try to make that choice visible before the next fault. Their success will depend on a detail that peak demand alone cannot show: what a qualifying large load does during the first 100 milliseconds of a grid disturbance.